Magandang araw po sa ating lahat na imbagnal daw kanya tayo amin. Good day to every one of us. So right now we're going to solve problems in DC Shunt Generators. In this video we will just be dealing with easy problems which are very important for us to be prepared to solve complex problems. But before solving problems we need to first understand how to establish the equations we will be needing. We don't need to memorize these equations. What we need is to understand the principle because that's what we will also apply to the other types of DC generators. These are applications of algebra, Kirchhoff's laws, Ohm's law, and power formula. It's very important for beginners to understand how to establish the necessary equations. This will also let us minimize the equations and formulas we need to memorize and remember. This is the typical circuit diagram of the DC shunt generator, but for this lesson, we will use this equivalent circuit diagram to simplify our analysis. Let us first identify each part. This is the armature where the generation of EMF happens. That's why we have here the EG or generated EMF. Here we have the brushes. They are representation of the pair of positive and negative brushes. Although in other generators they may have more than one pair, but they are represented by this pair only. Their function is to collect the generated EMF from the armature. There are problems involving voltage drops in these brushes, but some problems will give us negligible voltage drops in them. We have here the armature circuit resistance. In the actual machine, this resistance is in the armature, not on the outside. It's not even after the brushes. But to simplify our analysis, this resistance is taken out. Here we have the shunt field winding. It is connected in parallel with the armature circuit. This is a representation of the field coils around the field poles. These coils are connected in series, therefore the field circuit resistance present in this coil is the total resistance of the series field connected windings. This resistance is indicated as RSH. For some, it is just simply RF. And lastly, we have the terminals where we have the terminal voltage, VT, and where the load is connected. Some problems would involve feeder conductor resistance, but in most problems, this resistance is considered negligible. So now, let's establish the necessary equations we need to solve for the problems later. We will be using Kirchhoff's current law and Kirchhoff's voltage law, and again combined it with power formula and Ohm's law. We know the generator delivers electric power, and that power comes from the armature. So there is a current coming from the armature indicated as IA, or the armature current. Its direction will follow the conventional current flow, which is from positive to negative. At this part of the circuit, only the armature current flows. Then at this node, it is divided into two currents. One current goes to the shunt field winding, which is the field current or the shunt field current. The other current will flow to the load, which is the load current or the line current, indicated as IL. That's if when the generator has a load. During no load, the armature current will only be supplying the shunt field winding. And if we are going to analyze this, the armature current will be equal to the shunt field current. But again, that will happen if there is no load connected to the terminal of the generator. But if there's a load on its terminal, then IL will be present. During that time, IA will not be equal to ISH anymore. Another thing, armature current is always greater than the load current. Not all of this current will flow to the load. A part of it will be used to supply the shunt field winding. At this node, using Kirchhoff's current law, we have summation of current in equals summation of current out. Only the armature current is entering this node. Then the load current and shunt field current are exiting this node. Therefore, we have armature current equals shunt field current plus load current. This is our first equation, which in most of the computations involving DC generators, this is needed. But of course, do not memorize this equation because you do not need to. It is only derived by analyzing this circuit. Next is to establish the other equations, and now we will be using Kirchhoff's voltage law. There are several loops that we could establish here. The main loop is from the armature to the load. But of course, let's not forget to indicate the positive and negative terminals of each parameter here according to the direction of the currents. We already have here the positive and negative terminals of the brushes of the armature. At the armature circuit resistance, this is the first terminal where the armature current enters, so this will be the positive. And of course, this will be the negative where the armature current will be exiting the armature circuit resistance. At the load, we have here the positive at which the current IL enters, and of course, this will be the negative. At the shunt field winding, this is where ISH enters, so this will be the positive, and of course, this will be its negative. Now, going back to this loop, say loop 1, using Kirchhoff's voltage law, so we have Kirchhoff's voltage law at loop 1. First, we have the positive EG. Then the loop passes through the armature circuit resistance, that is negative. Multiply this by the current flowing through it, which is armature current IA. So we have negative IA times RA. Then we go to the terminal voltage, so we have here negative, so negative VT. And we equate this to 0 since we're going back to where we started at the armature. These are the two main equations that we will be using. Now, if we want to determine the value of IL, or the load current or line current, one way is we have the power formula for that. Power is equal to the current times voltage. For most of the problems, the power consumed by the load and the terminal voltage are given. Therefore, we can determine the load current. Deriving this formula, cross-multiply the voltage to the other side of the equation. We have current is equal to the power divided by the voltage, or the power consumed by the load divided by the terminal voltage. Another way to determine the load current is by using this formula. Power equals to the square of the current multiplied by the resistance if the power consumed by the load and its resistance are given. Deriving this equation, we have current is equal to the square root of power consumed by the load divided by the resistance. To determine the value of the ISH, or the shunt field current, if we will analyze this circuit, to determine ISH, or the shunt field current, we use Ohm's law. We have the shunt field current equals to the voltage of the shunt field divided by its resistance. But analyzing this circuit, the voltage across the shunt field resistance is equal to the terminal voltage because they are connected in parallel. So VSH equals to the terminal voltage. Therefore, we have ISH equals terminal voltage divided by the shunt field resistance. To also prove this, we can use this loop. It passes from the shunt field resistance to the terminal voltage. So let's say that this is loop 2. Kirchhoff's voltage law at loop 2. First, we have positive RSH, multiply that by the shunt field current. So that is positive ISH times RSH. Then the loop goes to the terminal voltage, so we have there negative, so that is negative VT, and equate that to 0. Transpose negative VT to the other side of the equation, we have positive VT. Cross-multiplying the shunt field resistance to the other side of the equation, we have ISH equals the terminal voltage divided by the shunt field resistance, which is just the same as what we have analyzed a while ago. This loop is also important when there is a rheostat connected in series with the field winding. Example, we have this circuit, so here is the rheostat. This is used to control the field current and is used for voltage regulation. The loop will pass from the shunt field resistance to the rheostat and to the terminal voltage. So let's say that this is loop 3. So Kirchhoff's voltage law at loop 3, we will arrive at this equation. So first we have positive RSH, multiply that by its current, ISH. So positive ISH times RSH. Then the loop passes to the rheostat. We have here positive. And since the rheostat and the shunt field are connected in series, therefore the value of their current are the same, which is the shunt field current. So we have positive shunt field current, multiply that by the resistance of the rheostat. Then of course, lastly, we go to the negative terminal voltage and equate that to 0. Then of course, we can just manipulate these equations to determine which are required. Again, you do not need to memorize these equations. It's only derived from this circuit using circuit analysis. So back to this circuit. Last loop that can be needed is this loop. It passes from the field circuit to the armature circuit. Or you can do it the other way around. So let's say that this is loop 4, Kirchhoff's voltage law at loop 4. First we have positive EG, then negative IA times RA, then minus ISH times RSH. So this is the equation from this loop. Again, that is positive EG minus IA times RA minus ISH times RSH equal to 0. So these are the equations we would need to solve problem depending upon the required of the problem. But again, you do not need to memorize these equations. We derive them by analyzing this circuit. So now we will solve problems. Please bear patience. We will do it step by step for beginners. We have here problem number 1. A 230 volt shunt generator has a field circuit resistance of 100 ohms. What is the field current when the generator operates at rated voltage? It's very important to understand the problem so we can solve it properly. We have here a shunt generator, so we already have the idea of its circuit diagram. It says here 230 volt shunt generator, meaning to say that 230 volts here is the terminal voltage of the generator. And the field circuit resistance RSH is equal to 100 ohms. We are asked to determine the field current of the generator, that is ISH. So analyzing this circuit, we will only need this part of the circuit. To determine the value of the shunt field current using Ohm's law, current equals voltage over resistance. For this problem, we have shunt field current equals the voltage across the shunt field circuit, divide this by its field resistance or the shunt field resistance. Take note that this is a shunt generator, therefore VSH equals to the terminal voltage. That's why we have shunt field current equals the terminal voltage, divide this by the shunt field resistance. Substitute the values. ISH equals 230 volts, divide this by 100 ohms. The answer is 2.3 amperes. So this is the value of the field current or the shunt field current when the generator operates at its rated voltage. Next problem, number 2. What is the field current of a 110 volt shunt generator if the field circuit resistance is 55 ohms? Again, we have a shunt generator, so therefore we already have the idea of what the circuit is. It says 110 volt shunt generator, so therefore the terminal voltage is equal to 110 volts. The field circuit resistance is 55 ohms. And we are asked to determine the field current, that is ISH. Again, using Ohm's law, current equals voltage over resistance. So for this problem, we have the shunt field current equals the voltage across the shunt field winding, divide this by the shunt field resistance. Again, the voltage across the field winding is equal to the terminal voltage since it is connected in parallel. So we have ISH equals VT all over RSH. Substituting the values, we have ISH equals 110 volts, divide this by 55 ohms. The value or the answer here is 2 amperes. Let's proceed to problem number 3. The shunt field winding of a 240 volt shunt generator has a resistance of 60 ohms. How much field rheostat resistance must be added to limit the field current to 3 amperes when the generator is operating at rated voltage? We have a 240 volt shunt generator, so 240 volts is its terminal voltage. The shunt field winding has 60 ohms resistance. We are asked to determine how much field rheostat resistance must be added to limit the field current to 3 amperes at rated voltage. Because if the field circuit does not have a rheostat, then computing for the field current, we have ISH equals VSH over RSH. We know that the shunt field voltage is equal to the terminal voltage, that is 240 volts. Substitute the values. Shunt field current equals 240 volts, divide this by 60 ohms. We have 4 amperes. The problem says that it is desired to limit the field current at 3 amperes. So now let's use this circuit diagram. The rheostat is connected in series with the field winding. And we will only analyze this part of the circuit, not including the armature for the computation. A while ago, we have established an equation using Kirchhoff's voltage law at this loop. But let's use another solution. Take note that the shunt field and the rheostat are connected in series. Therefore, we can use basic Ohm's law to solve this problem. Current equals voltage divided by resistance. For this problem, we have shunt field current equals shunt field voltage divided by the total resistance in the field circuit. Our total equals shunt field resistance plus the resistance of the rheostat. Substituting this equation to this equation, we have shunt field current equals VSH divided by the sum of shunt field resistance and the resistance of the rheostat. Cross multiplying the shunt field current to the other side of the equation, and also cross multiplying the sum of the shunt field resistance plus the resistance of the rheostat to the other side of the equation. So we have RSH plus R equals VSH all over ISH. And we already know that the voltage across the shunt field circuit is equal to the terminal voltage. So therefore we have terminal voltage divided by the shunt field current at the side of the equation. So this is the equation that we will use in order to determine the resistance of the rheostat. Take note that the shunt field resistance is given as 60 ohms, terminal voltage is 240 volts, and the desired field current is 3 amperes. Substituting those values in this equation, we have 60 ohms plus R equals 240 volts divided by 3 amperes. 240 volts divided by 3 amperes, that is 80 ohms. Transposing 60 ohms to the other side of the equation, we have R equals 80 ohms minus 60 ohms. Therefore, the field rheostat resistance is equal to 20 ohms. Let's proceed to problem number 4. A 220 volt shunt generator has a field circuit resistance of 100 ohms. A field rheostat is controlled in order to limit the field current to 2 amperes at rated voltage. How much resistance must be added using the field rheostat? This is similar to problem number 3. Again, it's important to solve similar problems for beginners to help us understand these problems. If you have more similar problems, then the better. But for this problem, we will use a different approach. Again, it is desired to limit the field current to 2 amperes at rated voltage. The terminal voltage of the shunt generator is 220 volts. The shunt field resistance is 100 ohms. We are asked to determine the resistance at the field rheostat. Of course, we will still use this circuit diagram. Take note, if the resistance of the field rheostat is 0, therefore the field current will not be equivalent to 2 amperes. Its value would be ISH equals VSH, which is equivalent to the terminal voltage, divided by RSH. 220 volts divided by 100 ohms, that is 2.2 amperes. The 0.2 ampere difference to 2 ampere would seem to be quite small, but in actual operation it has a contribution, depending upon the operation of the generator. Anyway, to solve this problem, let's establish a loop passing from the shunt field to the field rheostat and to the terminal voltage. Say that is loop 1. So Kirchhoff's voltage law at loop 1, first we have positive RSH, multiply that by ISH. So that is positive ISH times RSH, plus the resistance of the rheostat, multiply that by the current flowing through it, which is also the shunt field current, since they are connected in series. So therefore we have positive ISH times R, then minus the terminal voltage equal to 0. Let's transpose ISH times RSH and negative VT to the other side of the equation, leaving ISH and R in this side of the equation. Therefore we have ISH times R equals the terminal voltage minus ISH times RSH. Cross multiply the shunt field current to the other side of the equation. We have the resistance of the field rheostat equals the terminal voltage minus ISH times RSH, divide this by ISH. We have the value for the terminal voltage, that is 220 volts. Shunt field current is 2 amperes. Shunt field resistance is 100 ohms. Substitute those values. We have 220 volts minus 2 amperes times 100. Divide this by 2 amperes. The answer is 10 ohms. Let's solve problem number 5. A 230 volt shunt generator has a field circuit resistance of 75 ohms. What is the armature current when the generator supplies 25 amperes to a load? Again, we have a shunt generator. For this problem, we will be solving for the armature current. The load current is given as 25 amperes. Terminal voltage is 230 volts. and field circuit resistance is 75 ohms. There are several ways on how to solve for the armature current, but for this problem, if we will analyze, we will solve the armature current IA through Kirchhoff's current law since the armature circuit resistance is not given. So we cannot use Kirchhoff's voltage law. Solving this problem by Kirchhoff's current law, we have here a node where there are currents entering and exiting. You can still use this node at the bottom, but typically we use this node. So let's indicate this node as node A. If you want to indicate this as node X, then do so. But anyway, Kirchhoff's current law at node A, summation of current in equals summation of current out. Armature current is entering this node, and the load current and shunt field current are exiting this node. Therefore, we have IA equals IL plus ISH. IL is already given, that is 25 amperes. And we can solve shunt field current using Ohm's law at this part of the circuit. ISH equals VSH over RSH. Again, the shunt field voltage is equal to the terminal voltage, that is 230 volts. Shunt field resistance is 75 ohms. Substitute those values. We have ISH equals 230 volts divided by 75 ohms. That is 3.067 amperes. Now we can substitute this value to this equation. Therefore, IA equals 25 amperes for the load current plus 3.067 amperes. This is equivalent to 28.067 amperes. Let's solve problem number 6. A 240 volt shunt generator delivers 60 amperes to a load. If the field circuit resistance is 120 ohms, what is the value of armature current? This is similar to problem number 5. Again, we have a shunt generator. Terminal voltage is 240 volts. Load current is 60 amperes. Shunt field resistance is 120 ohms. And we are asked to determine the value of the armature current. Analyzing this problem, we use Kirchhoff's law at this node. Let's indicate this as node A. Kirchhoff's current law at node A, that is summation of current in equals summation of current out. Analyzing at this node, IA is entering, IL and ISH are exiting. So we have IA equals IL plus ISH. Again, the load current is given as 60 amperes. Before we can solve the armature current, let's solve the shunt field current first. Analyzing this part of the circuit using basic Ohm's law, we have ISH equals VSH over RSH. RSH is already given as 120 ohms. And the terminal voltage is equal to the voltage across the shunt field winding. That is 240 volts. Substituting those values, we have 240 volts divided by 120 ohms. The answer is 2 amperes. Now that we have the value for the shunt field current, let's substitute this value to this equation. Again, IL is 60 amperes. So we have IA equals 60 amperes plus 2 amperes. Therefore, the armature current is equal to 62 amperes. Let's proceed to problem number 7. A shunt generator is rated 12 kilowatts at 240 volts. Letter A, what is the full load current? Letter B, what is the field current if the field circuit resistance is 100 ohms? And letter C, what is the full load armature current? So again, we have a shunt generator. And we are asked to determine the full load current, the field current, and the full load armature current. The terminal voltage of this generator is 240 volts. And its rated power is 12 kilowatts or 12,000 watts. To determine the full load current, from the power formula, power equals current times voltage. Cross multiply the voltage to the other side of the equation. We have current is equal to power divided by the voltage. But of course, for this problem, we are asked to determine the full load current. So therefore, load current equals the rated power of this generator divided by its terminal voltage. Substitute 12 kilowatts and 240 volts in this equation. We have 12 kilowatts divided by 240 volts. The answer is 50 amperes. Next, we determine letter B, that is the field current. Again, by using Ohm's law, we have shunt field current equals the shunt field voltage divided by the shunt field resistance. Again, the shunt field voltage is equal to the terminal voltage, so substitute those values. We have 240 volts divided by 100 ohms. The answer is 2.4 amperes. Now that we have these values, we can determine the full load armature current. Again, from this node, say node A, Kirchhoff's current law at node A, we have summation of current in equals summation of current out. Current IA is entering this node and currents IL and ISH are exiting this node. That's why we have IA equals IL plus ISH. IL is 50 amperes and ISH is 2.4. Substitute these values. We have 50 amperes plus 2.4 amperes. The answer is armature current is equal to 52.4 amperes. Problem number 8, we have a 50 kilowatts 220 volt shunt generator has a field circuit resistance of 150 ohms. Determine the value of the full load current, field current, and armature current at full load. Again, we have a shunt generator. Its rated power is 50 kilowatts and its terminal voltage is 220 volts. Field circuit resistance is given as 150 ohms. First, we will determine its full load current. Again, from the formula, power equals current times voltage. Cross multiply voltage to the other side of the equation. We have current is equal to power divided by voltage. And for this problem, we are asked to determine the full load current. Therefore, we have the full load current of the generator equals its rated power divided by the terminal voltage. Substitute 50 kilowatts and 220 volts. We have 50 kilowatts divided by 220 volts is equal to 227.273 amperes. So this is the value of its full load current. Next, we determine its field current, ISH. Again, analyzing this circuit by using Ohm's law. Shunt field current equals shunt field voltage divided by the shunt field resistance. Shunt field voltage is equal to the terminal voltage, while shunt field circuit resistance is 150 ohms. Substitute those values. We have 220 volts divided by 150 ohms. This is equal to 1.467 amperes. And for the armature current, at this node, let's say node A, Kirchhoff's current law at node A, summation of current in equals summation of current out. IA equals IL plus ISH. Substitute the values of load current and shunt field current to this equation. We have IA equals 227.273 amperes plus 1.467 amperes. The answer is 228.74 amperes. Let's proceed to problem number 9. The terminal voltage of a shunt generator is 115 volts when the generated EMF is 119 volts. And the armature current is 20 amperes. What is the armature circuit resistance? We have a shunt generator. The terminal voltage is 115 volts. The generated EMF is equal to 119 volts. And of course, the armature current IA is equal to 20 amperes. We are asked to determine its armature circuit resistance, RA. Understanding this problem, we will just be dealing with this loop. It passes from the armature circuit to the terminal voltage. Let's say this is loop 1, so therefore Kirchhoff's voltage law at loop 1, we begin at the generated EMF, that is positive. Next we have negative RA, multiply that by IA. And lastly, negative terminal voltage. So we have this equation, positive generated EMF minus IA times RA minus the terminal voltage equal to 0. Armature circuit resistance is required, so therefore we transpose negative IARA to the other side of the equation. So we have EG minus VT equals positive IA times RA. Then next, cross multiply IA to the other side of the equation. We have EG minus VT divided by IA equals RA. The generated EMF is 119 volts and the terminal voltage is 115 volts. Current IA equals 20 amperes, so we substitute those values. 119 volts minus 115 volts divided by 20 amperes. Armature circuit resistance equals 0.2 ohm. Next problem, number 10. The generated EMF of a 240 volts generator is 255 volts when the armature current is 50 amperes. Determine the armature circuit resistance. This is a similar problem with number 9. For this problem, it is not being said that this is a shunt generator, but we assume that this is a shunt generator. The generated EMF is 255 volts and the terminal voltage is 240 volts. The armature current is 50 amperes. We will determine the value of the armature circuit resistance RA. Again, for this problem, we use this loop. Say that is loop number 1. Kirchhoff's voltage law at loop number 1, we have positive EG minus IA times RA minus VT. So we have positive EG minus IA times RA minus VT equals 0. Again, we transpose negative IA RA to the other side of the equation since we are going to determine the armature circuit resistance. So we have positive EG minus VT equals positive IA RA. Cross multiplying current IA to the other side of the equation, we have positive EG minus VT divided by IA equals RA. Again, the generated EMF is 255 volts. The terminal voltage is 240 volts and current IA equals 50 amperes. Substitute those values. 255 volts minus 240 volts divided by 50 amperes. Armature circuit resistance equals 0.3 ohm. Now let's proceed to problem number 11. The terminal voltage of a 75 kilowatts shunt generator is 600 volts at rated load. The resistance of the shunt field circuit is 150 ohms and the armature circuit resistance is 0.1 ohm. Determine the generated EMF. Again, we have a shunt generator. Its terminal voltage is 600 volts. Its rated power is 75 kilowatts. The armature circuit resistance is 0.1 ohm and the shunt field circuit resistance is 150 ohms. We are asked to determine what is the generated EMF. For this problem, we will be needing this loop where we will be solving this problem based from the given values. So let's say that this is loop number 1. Kirchhoff's voltage law at loop number 1, we have first positive EG. The next, negative RA, multiply this by IA. Then lastly, we have negative VT. Therefore, we have positive EG minus IA times RA minus VT equals 0. And since the generated EMF is required, therefore, we transpose negative IA RA minus VT to the other side of the equation. So we have generated EMF equals VT plus IA RA. So let's say that this is equation number 1. The terminal voltage is already given, that is 600 volts, and the armature circuit resistance RA is also given, that is 0.1 ohm. Current IA is not yet given, therefore we need to determine its value. To determine its value, let's have this node, say node A. Kirchhoff's current law at node A, summation of current in equals summation of current out. IA is entering this node and IL and ISH are exiting this node. Therefore, we have IA equals IL plus ISH. Say this is equation number 2. IL and ISH are not given, but we can determine their values. First, we determine the value of IL. We use this formula. Again, we do not need to memorize this formula. It is only being derived from power equals current times voltage. The rated power is 75 kilowatts and the terminal voltage is 600 volts. Substitute those values. We have 75 kilowatts, or this is 75,000 watts. Divide this by 600 volts. IL equals 125 amperes. Now that we have the load current, let's determine the value of ISH, or the shunt field current. Analyzing this circuit using Ohm's law, we have shunt field current equals shunt field voltage divided this by shunt field resistance. And of course, we know that the shunt field voltage equals the terminal voltage since they are connected in parallel. So substitute 600 volts and 150 ohms to this equation. We have 600 volts divided this by 150 ohms. The answer is 4 amperes. Now that we have the values for IL and ISH, let's substitute those values to this equation, equation number 2. So armature current equals 125 amperes plus 4 amperes. This is equal to 129 amperes. And now that we have the value of the armature current, let us substitute it to equation number 1. Since terminal voltage and armature circuit resistance are given. Therefore, the generated EMF equals 600 volts plus 129 amperes times 0.1 ohm. The answer is 612.9 volts. Now we go to problem number 12. A 20 kilowatts 220 volt shunt generator has an armature circuit resistance of 0.15 ohm and a shunt field circuit resistance of 120 ohms. Determine the generated EMF at full load. From the diagram of the shunt generator, again, we are asked to determine the generated EMF. The terminal voltage is 220 volts. RA is 0.15 ohm. The rated power is 20 kilowatts and the shunt field resistance is 120 ohms. Basing from the given values, we need this loop, say loop number 1. Kirchhoff's voltage law at loop number 1, again we have this equation. It starts from the generated EMF, that's positive. Next we have negative IA times RA, that's the voltage drop in the winding of the armature. Then we have negative VT equals 0. Again, since EG is required, we transpose negative IARA minus VT to the other side of the equation. Therefore, we have the generated EMF equals the terminal voltage plus IARA. This is equation number 1. Terminal voltage is given as 220 volts and armature circuit resistance is 0.15 ohm. We will still determine the value of IA. To determine IA, let's have this node, node A. Kirchhoff's current law at node A, summation of current in equals summation of current out. That is IA equals IL plus ISH. Say this is equation number 2. Why do we say that we do not need to memorize these equations? It's because we might be confused when we will be dealing with DC motors. These equations can be taken by analyzing this circuit diagram. Anyway, to determine the value of armature current, we still need to determine the value of the load current and the shunt field current. First, by using this derived equation, IL equals PL over VT. PL is given as 20 kilowatts and terminal voltage is 220 volts. Substitute those values. We have IL equals 20,000 watts or 20 kilowatts. Divide this by 220 volts. IL is 90.909 amperes. Next, let's determine what is ISH. Analyzing this circuit using Ohm's law, ISH equals shunt field voltage divided this by shunt field circuit resistance. Shunt field voltage is the same as the terminal voltage, 220 volts. Divide this by 120 ohms. The answer is 1.833 amperes. Now that we have these values, IL and ISH, substitute them to equation number 2. Therefore, we have IA equals 90.909 amperes plus 1.833 amperes. Armature current is 92.742 amperes. And of course, let's substitute this value to this equation, equation number 1. The generated EMF equals 220 volts plus 92.742 amperes. Multiply this by 0.15 ohm. The answer for the generated EMF is equal to 233.911 volts. Problem number 13. A 100 kilowatts 230 volts shunt generator has an armature circuit resistance of 0.15 ohm and a shunt field circuit resistance of 100 ohms. Determine the generated EMF at half load. This shunt generator is rated 230 volts terminal voltage and its power is rated at 100 kilowatts. The armature circuit resistance is 0.15 ohm and the shunt field circuit resistance is 100 ohms. We are asked to determine the generated EMF at half load. So to determine the half load of this generator, that is simply multiplying its rated power, 100 kilowatts, by 1/2. So we have 1/2 times 100 kilowatts. This is 50 kilowatts. The generated EMF at half load will be different from the value of the generated EMF at full load. Basing from the problems, again, we use this loop. Say that is loop number 1. Kirchhoff's voltage law at loop number 1. So we have this equation. Transpose negative IA times RA minus VT to the other side of the equation. We have the generated EMF equals positive VT plus IA times RA. Say this is equation number 1. Terminal voltage is already given as 230 volts and armature circuit resistance is 0.15 ohm. We still need to determine what is the value of armature current. To determine armature current, let's say we have this node, node A. Kirchhoff's current law at node A, summation of current in equals summation of current out. We have IA equals IL plus ISH. Say this is equation number 2. Now let's determine IL. IL equals the power delivered by the generator, divide this by the terminal voltage. We will not be using 100 kilowatts for this, but we will be using 50 kilowatts instead. So substitute that, 50 kilowatts, divide this by the terminal voltage, which is 230 volts. The answer is 217.391 amperes. Now let's determine the shunt field current by using Ohm's law. Shunt field voltage equals terminal voltage, that is also 230 volts. Shunt field resistance is 100 ohms. Substitute those values. 230 volts, divide this by 100 ohms. Shunt field current equals 2.3 amperes. Substitute the values of IL and ISH to equation number 2. So we have IA equals 217.391 amperes plus 2.3 amperes. We have armature current equals 219.691 amperes. Using this value, substitute it to equation number 1. The generated EMF equals 230 volts plus 219.691 amperes times 0.15 ohm. EG equals 262.954 volts. Now we have problem number 14. A 90 kilowatts 240 volts shunt generator has an armature and field circuit resistances of 0.12 ohm and 120 ohms respectively. Determine the generated EMF if this machine is delivering 1/3 of its rated capacity. So we have a 240 volts shunt generator. Its rated capacity is 90 kilowatts. The armature circuit resistance RA is given as 0.12 ohm and the shunt field circuit resistance is 120 ohms. We will determine the generated EMF if this machine is delivering 1/3 of its rated capacity only. To do that, let's multiply the rated capacity by 1/3. So 1/3 times 90 kilowatts, the answer is 30 kilowatts only. Again, there's a difference between the generated EMF if the generator is delivering different powers. So let's determine the generated EMF if this generator is delivering 30 kilowatts. Analyzing this problem, we need this loop, say loop number 1. Kirchhoff's voltage law at loop number 1, we have positive EG minus IARA minus VT equals 0. Again, we transpose negative IA times RA minus VT to the other side of the equation. So generated EMF equals terminal voltage plus IA times RA. This is equation number 1. We already have the terminal voltage, that is 240 volts. And the armature circuit resistance RA, that is 0.12 ohm. We need to determine the value of IA first before we can determine the generated EMF. So to do that, let's have here node A. So Kirchhoff's current law at node A, that is summation of current in equals summation of current out. IA equals IL plus ISH. This is equation number 2. For IL, we use this formula. Derived from power equals current times voltage. We will be using the 30 kilowatts instead of using the 90 kilowatts to determine its load current at 1/3 of its rated capacity. So we have 30 kilowatts, divide this by 240 volts, the value is 125 amperes. Now let's determine shunt field current also. Analyzing this circuit using Ohm's law, we have ISH equals VSH over RSH. The shunt field voltage is equal to the terminal voltage, so we have 240 volts, divide this by 120 ohms. The answer is 2 amperes. Now that we have IL and ISH, let's substitute them to equation number 2. IA or armature current equals 125 amperes plus 2 amperes. The value is 127 amperes. Now that we have the value for the armature current, let's substitute it to equation number 1. Generated EMF equals 240 volts plus 127 amperes times 0.12 ohm. The value is 255.24 volts. Problem number 15. In a 50 kilowatts, 250 volts shunt generator, 258 volts are generated in the armature when the generator delivers rated load at rated voltage. The shunt field current is 4 amperes. Determine the resistance of the armature. We have a 250 volts shunt generator rated 50 kilowatts. The generated EMF amounts to 258 volts. Shunt field current ISH is 4 amperes. We are asked to determine the resistance of the armature, that is RA. For this problem, we need this loop and this node. So let's say node A and loop 1. First, let's establish an equation in loop number 1. Positive EG minus IARA minus VT equals 0. The required variable is the resistance RA. So we transpose negative IARA to the other side of the equation. Therefore, we have positive EG minus VT equals positive IARA. Cross multiplying IA to the other side of the equation, we have positive EG minus VT divided by IA equals the armature circuit resistance. So this is the equation that we will be using to determine the armature circuit resistance. Let's say that this is equation number 1. We already have the value for generated EMF and the terminal voltage. So first, we need to determine the value of the armature current. To do that, let's have here node A. Kirchhoff's current law at node A, summation of current in equals summation of current out. We have this equation. IA equals IL plus ISH. This is equation number 2. We already have the value for ISH, that is 4 amperes. We will determine first the value of IL. From this formula, substitute 50 kilowatts and 250 volts here. Therefore, we have 50 kilowatts divided by 250 volts. IL amounts to 200 amperes. And substitute IL and ISH to this equation, equation number 2. Therefore, IA equals 200 amperes plus 4 amperes. Armature current is 204 amperes. Now that we have the value for the armature current, let's substitute it to equation number 1. RA equals 258 volts for the generated EMF minus 250 volts for the terminal voltage. Divide this by 204 amperes. RA, or the armature circuit resistance, is 0.0392 ohm. Or this could be rounded off to 0.04 ohm. Let's have the last problem. Problem number 16. A 200 kilowatts, 440 volts shunt generator generates 450 volts in the armature when delivering its rated capacity. The field circuit resistance, or the field resistance, is 70 ohms. Determine the resistance of the armature. The terminal voltage of this shunt generator is 440 volts. Its rated capacity is 200 kilowatts. The generated EMF inside the armature is 450 volts. Shunt field circuit resistance is 70 ohms. We are asked to determine the resistance of the armature, that is RA. Again, we will be needing this node and this loop for this problem. Now let's establish the equations that we will be needing. Kirchhoff's voltage law at loop number 1, we have this equation. Positive EG minus IA times RA minus VT equals 0, transposing negative IA times RA to the other side of the equation. We have EG minus VT equals positive IA times RA. Cross multiplying IA to the other side of the equation, we have EG minus VT divided by IA equals armature circuit resistance. So this is the equation that we will be needing to determine the armature circuit resistance. Say this is equation number 1. We already have the value for the generated EMF, that is 450 volts, and the terminal voltage is 440 volts. But we still need to determine the current IA. To do that, using node A, Kirchhoff's current law at node A, we will arrive at this equation. Equation number 2, IA equals IL plus ISH. We first need to determine the value of IL and ISH. For IL, we use this derived formula from power equals current times voltage. The rated power of this generator is 200 kilowatts and the terminal voltage is 440 volts. Substitute those values. We have 200 kilowatts divided by 440 volts. IL equals to 454.545 amperes. To determine ISH, analyzing this circuit by using Ohm's law, we have ISH equals VSH over RSH. The shunt field voltage is equal to the terminal voltage, that is 440 volts. The value for the shunt field resistance is 70 ohms. Therefore, ISH equals 6.286 amperes. Now let's substitute these values to equation number 2. Armature current equals 454.545 amperes plus 6.286 amperes. Armature current is 460.831 amperes. And of course, now that we have the value for the armature current, let's substitute it to equation number 1 to determine armature circuit resistance. RA equals 450 minus 440 volts divided by 460.831 amperes. Armature circuit resistance is equal to 0.0217 ohm. Hopefully, we learned something today. Again, in order to solve these problems properly, we need to first analyze them and understand them. Thank you so much for watching. Good day to every one of us. Magandang araw po sa ating lahat. Naimbag nga aldaw kanya tayo. Amin.